Hello, we're going to be looking at a way to express pi as an infinite series today. So pi is greater than 3 because if you bisect polygons, you receive a range for pi. Here we have a regular hexagon with a side length of 1. You would then have a perimeter of 6 for that. And using logic, we can clearly see that the circumference of the circle that's circumscribed is greater than the perimeter of that regular hexagon. So pi must be greater than 6 divided by 2, or in other words, pi is greater than 3. And pi is also less than 4 because if you add a square around that circle, that square has a perimeter of 8. And the perimeter of the square has to be greater than the perimeter of that circle, so pi is less than 8 divided by 2, or in other words, pi is less than 4. We know that pi is between 3 and 4 now, but we need to have more accuracy than that. And in 250 BC, Archimedes came up with this expression over here, and he used the same method of bisecting and stuff, but he did it with a dodecagon instead, which is a 12-sided polygon. So you can do this with any polygon basically, but the more sides you have in your polygon, the more digits of pi that need to be computed. And the more sides you do, the crazier it gets, and mathematicians went crazy having this competition over it. But then Isaac Newton showed up with his binomial theorem way, and this made things so much easier. So he and this other guy named John Wallis, they both saw that the equation of the unit circle can be rewritten in terms of y like this. And then a quick side note, area of unit circle is pi. We need to remember that for later. But anyways, when they did, they realized that it equals the hemisphere on top. And in 1655, there wasn't integrals and the binomial theorem wasn't a thing. So this poor guy, John Wallis, he had to do this entire thing by himself on his own. And then this is just how we would write it today using integrals. Anyways, Isaac Newton solved this more efficiently using the binomial theorem, more efficiently than people ever have before. Then this down here is a solution he got from doing it, and then this is his famous infinite series for pi. And we're like, okay, so if this was his right-hand side, what's his left-hand side? Well, hint, hint, this was his famous infinite series for pi, so your left-hand side must have pi in it. And so he sets this equal to pi over 4 on the left-hand side because he had just invented something called calculus, or what he likes to call the theory of fluxions. And in calculus, when you integrate under the curve from 0 to 1, the area that you're computing is pi over 4. So that's your left-hand side. And this over here, remember, is the infinite series, which you got from doing the binomial theorem. And so multiplying by 4 over here would help you simplify this thing. And basic integration is pretty simple. It's just taking your power of x and raising that by 1 and dividing by that new power. So if it's x squared here, that's x cubed over 3. You're raising it by 1, dividing it by that same power. And when he does, he gets a really good converging series, and he likes it. It's a good series, and you also substitute x equals 1 into it because you're integrating under the curve from 0 to 1. Yeah. But he wonders if he can integrate from 0 to 1/2. And why would he want to do that? Well, the reason why he did is because he knows that integrating from 0 to 1/2 will make his series converge by an extra factor of 1/2. And this will mean faster and more digits of pi in less time thing. So efficiency reasons. So here, the only difference is that you have to use x equals 1/2 instead. And then the area under the curve is also different. So, the area under the curve is like this thing, and you have a 30-degree sector, which has an area of pi over 12, and then this is a right triangle with a base of 1, and then a height of root 3 over 2, and these multiplied here will be root 3 over 8, and that plus pi over 12 will be your left-hand side. Meanwhile, our right-hand side is the integration stuff again, which is, stuff that we had from the binomial theorem. And now, when you integrate with 1/2 instead, everything is the same. You just have an you substitute x equals 1/2 in. But again, you have 2 being raised up to 3 and dividing by 3 again, which is the same as multiplying by 1/3, So it's the same thing. And this now will leave him with a faster and a better way to calculate pi using his really cool infinite series. And the end. Thank you for listening to me today.